Hello viewers, welcome to this lecture on discrete systems. So, in this lecture we will see some results on the state transition matrix, solution of discrete system and the controllability of discrete systems, which is these results are analogous to the continuous dynamical systems and control systems. So, earlier we have seen the continuous control systems of the form dx by dt equal to a xt and b ut. So, here A may be a constant matrix or time varying matrix, similarly B may be constant or time varying. So, this continuous control system has solution x of t equal to phi t t0 x0 plus integral t0 to t phi t s b u s ds. So, this is the solution of the control system for the initial condition x of t0 equal to x0. Now, we have also introduced some discrete control system or discrete dynamical system, which is of the form x of k plus 1 equal to a of k x of k plus b of k u of k is a discrete control system, where k is varying from k0 plus 1 etc. k0 plus n. So, we have the discrete control system in this form. So, if we call it as 1 and this as 2. Now, how to write the solution of the discrete system, and we can also see what is the connection between a continuous control system and a discrete control system. So, we can formulate various discrete control system on its own. Various problem like population dynamics can be, for example, written as x of k plus 1 equal to some constant times x of k. So, this may be representing or a mathematical model for a population dynamics or some such similar problems, as we have seen population dynamics for a simple model of population dynamics in terms of a continuous dynamical system can be written like this, where A is the rate of increase of the population, and here also alpha is the rate of increase of the population, and so it gives a simple mathematical model whether it is continuous or discrete system. But certain problems, for certain problems discrete systems are more suitable, and certain problems continuous systems are more, continuous models are more suitable. Similarly, if we have a continuous model and if you want to solve it using a digital computer, in that case we have to convert this continuous system into a discrete system. So, we can also find such relation in the following way. So, if we consider let t naught, that is the initial time instant which we have taken, if you write it as k naught times h, where h is a small time instant which we take, and k naught is an integer, such that k naught is an integer and h is increment in time. And if you are interested in the values of x of t at various instances of time, let us say let t I, it is equal to k naught plus I into h for I is equal to 0, 1, 2, 3 etc. So, when we substitute I values differently, we will get the discrete points from T0, T1, T2 etc., and the time increment is h here in this. So, if now if u of t, because while doing or while applying a control in a practical problem, it is not possible to give the control in a continuous fashion, but we can give it in a discrete time instance. So, u of t I, we assume that it is equal to, sorry, u of t is equal to u of t I for the interval t I less than or equal to t less than t I plus 1. So, if we assume this way, the control is applied in a discrete fashion for this continuous control system, then the solution of the system can be written in this following way. The solution, for example, at u of t1, the solution at t equal to t1, that is equal to x of t1 is written as phi of t1 comma t0 into x0 plus integral t0 to t1 phi of t1 comma s b u s ds, which is same as e to the power a into t1 minus t0 into x0 plus integral t0 and t0 plus h. This is e to the power a into t0 plus h minus s b. Now, us in the interval t0 to t1 is u of t0, because we are assuming that u of t is measured in a discrete fashion. So, u of t equal to u of t I in this interval. So, we substitute u of s to be like this in the interval t0 to t0 plus h, and this is nothing but e to the power a h, t1 minus t0 is h into x0 plus, here now we can convert this into the following way. S is between t0 to t1. So, if we substitute S is equal to t0 plus h, sorry, t0 plus theta, where theta is between 0 less than or equal to theta less than h. So, because t is or s is between t0 to t1, so we can substitute this way. So, if you substitute s is equal to t0 plus theta here, t0 gets cancelled. So, this will be equal to e to the power a into h minus theta, and this is varying from t0 to t0 plus h, b into ds into u of t0, this expression. So, this further can be written as, the right hand side is e to the power a h into x0 plus, now if we convert this integral in terms of d theta here, So, ds is equal to d theta, and when s is equal to t naught, theta is 0, and here it is h 0 to h e to the power a into h minus theta b into d theta multiplied by u of t 0. So, similarly we can call this as the matrix E. E to the power a h can be called as a matrix E into x 0, and integral 0 to h of this expression we can call it as f into u of t naught. So, in the similar way we can calculate x of, so this is nothing but x of t 1 is given by this expression. Similarly, we can write x of t 2 in the place of t 1. If you put t 2 here, it will be phi of t 2 comma t 1 because initial position is t 1, initial time is t 1, final time is t 2 into x of t 1 plus integral t 1 to t 2 of this similar expression phi of t 2 comma s into b u s ds. So, here u value is u of t 1, that is a constant throughout the interval t 1 to t 2. So, that will be out of the integration. So, again we can see the same thing in the place of e to the power a into t 2 minus t 1. So, it will also be equal to e power a into h x of t 1 plus, here also we will get the same thing, e to the power a into h minus theta b d theta, and u of s is u of t 1. So, we can see that the expression is again E matrix into x of t 1 plus this matrix is same f into u of t 1. So, if you replace this t 1, t 2, t 3 etc. by some the suffix itself. So, this implies that in general we can write x of t suffix k plus 1 if you write, but we can replace it by x of k plus 1 just as a notation. X of k plus 1, it means x of t suffix k plus 1, that is equal to E into x of k, this matrix into x at t suffix k plus f into u of k. So, we will get a discrete control system in this particular fashion, and this h is the time instant at which we find the values of x as well as use the control at these time instances for this control system. So, when we solve a continuous control system using a computer, we can convert that system into a discrete system and then solve in a discrete fashion. So, this will give various simpler results for solving a discrete continuous control system in the form of discrete system as follows. So, here we will see various analogous results as in the case of continuous system. For example, the state transition matrix we have defined for a continuous system earlier. So, similarly we can define it here. So, consider the simple system x of k plus 1 equal to a x of k, where the time instances are k equal to k0 plus 1 etc. Now, repeatedly applying the equation 1, x at k0 plus 1 is a x k0 and x of k0 plus 2 is a square k0 a square x of k0, and similarly x of k0 plus n, it can be easily seen that it is a to the power capital N x of k0. Capital N can be written as k0 plus n minus k0. So, x of k0 plus n equal to a power n x of k0, n can be written as k0 plus n minus k0. So, we get, and if you substitute k equal to k0 plus n, and the notation phi of kl means a to the power k minus l. If you use this notation, then we can write the solution x of k equal to phi of k comma k0 into x of k0. So, it looks similar to the continuous system state transition matrix. So, we will see the analogous result of that one. Earlier we have seen phi of t0 is the state transition matrix for a continuous system, and if it is a constant matrix, we have seen it is equal to e to the power a into t minus t0. Otherwise, we use it use the Peano-Becker series to find the state transition matrix. But here in the discrete system, if A is a constant matrix, the state transition matrix is phi of k0 is a to the power k minus k0, and the property of continuous system we have seen d by dt of phi t t0 is a into phi t t0. So, say similar result in the discrete is phi of k plus 1 comma k0 is a times phi of k k0, that can be directly seen from here. If you put k plus 1 here, it will be a to the power k plus 1 minus k0, which is a times a to the power k minus k0, and this first one. And if you put both variables are same, k and k equal to k0, we will get a to the power 0, which is the identity matrix. And if you reverse this, a k minus k0 minus k, that is nothing but a k minus k0, its inverse is nothing but a to the power k0 minus k. So, we get this third result, and fourth can be easily verified. So, these four properties are analogous to the continuous case. Now, if you consider the control system x of k plus 1 equal to a x k plus b u of k for this time instances, it can be easily verified by substituting one by one, starting from k0. So, x of k0 plus 1 is a x k0 plus b u k0, and substituting k0 plus 2 here it will be k0 plus 1 plus b u of k0 plus 1 etc. So, we will get the formula easily, a x of k0 plus n, we will get a to the power n x of k0 plus this quantity, which can be written in the similar as we have seen in the previous case. N can be written as k0 plus n minus k0. So, by using the notation phi of kl is a to the power k minus l, we get the formula x of k, where k is k0 plus n, is equal to, this is phi of k comma k0, this into x of k0 plus the remaining portion can be written in the summation I is equal to k0 to k minus 1 of phi of k comma I plus 1 into b ui. So, this is the formula, and it is analogous to the formula for the continuous case. X of t is phi of t t0 x0 plus integral t0 to t phi of t s b u s d s. So, instead of integral we have summation and the discrete points we are using for the formula for the solution of a discrete system. Now, if you take non-autonomous system where A is not a constant, we can derive in a similar fashion. Only thing is A of k should be replaced at every place. So, x of k0 plus 1 is A of k0 into x of k0, x of k0 plus 2 we can get A of k0 plus 1 A of k0 into x of k0. So, for k0 plus n, it is clear that the right hand side we will start with A of k0 plus n minus 1 and then n minus 2 etc. up to the initial point k0. So, we will get this result x of k0 plus capital N will be equal to A of k0 plus n minus 1 and k0 plus n minus 2 etc. up to the initial point, that is k0, and then multiplied by x of k0. So, in general we can give the notation phi of k0 plus n comma m. It means we will start the A of k0 plus n minus 1 and then end with the last integer m here. So, this gives the state transition matrix for the time varying matrix here. And if you give the notation k equal to k0 plus n, we get the formula phi of k m is A k minus 1 up to A of m, and the solution 9 is written as x of k equal to phi of k k0 into x of k0. So, now we have to note here, if you write phi of m comma k, here m is less than k is greater than m when we write like this. So, k minus 1, k minus 2 up to m it can decrease, but when we write phi of m comma k, we cannot make use of a similar formula. We cannot start with m minus 1, m minus 2 and we cannot end at the point k here because m is less than k. So, we have to make how to write analogous to the continuous system. Continuous system we always write phi of t s inverse, it is equal to phi of s comma t. So, we do not consider, we do not bother about the t greater than s or less than s. In all cases we can write in this particular fashion, but here it is not possible to use this notation as it is here. So, we have to consider like this. So, phi inverse of k comma m is from the definition of phi of k comma m. If you take inverse both sides, we will get A inverse m first, A inverse m minus 1 etc. The last will be A inverse k minus 1. So, that is the straightforward formula. Phi inverse of k comma m is given by equation 11, but we will give a notation for this to be phi of m comma k. So, it is not directly using the definition of phi, but it is only a notation for phi inverse k comma m. We will write it as phi of m comma k, and the property similar to the continuous case, phi of k plus 1 m is given by this expression, which is same as A of k into phi of k comma m. So, we can prove all the 4 properties of the state transition matrix using these notations. So, whether it is a autonomous case or non-autonomous case, the 4 properties of the state transition matrix is proved in this way using this particular notation. So, now let us illustrate with an example how to solve a discrete dynamical system. So, let us consider a second order system. x1 of k plus 1 is minus x1 k plus k times x2 of k, and x2 of k plus 1 is 2 times x2 of k. Initial condition is x1 0 equal to x suffix 1 and x2 of 0 is x suffix 2, two numbers. So, now here the matrix A is a constant, it is a time varying matrix, because A is minus 1, k and 0, 2. So, k is varying, it is A of k is equal to this. So, it is a dynamical system, and the initial condition x naught, it is nothing but x1 x2, the vector is given, x at 0 is given by this expression. Now, we can solve the equation directly by using the Z transform, taking Z transform both sides of the first equation, of the second equation. So, we will get x Z transform of x2 of k plus 1, that is equal to 2 times Z transform of x2 of k, and using the formulas of Z transform, we will get Z into the Z transform of x2 minus x2 at 0 equal to 2 times Z transform of x2, and so x2, the Z transform of x2 is given by Z minus 2 into x2 of 0. So, by using the inverse Z transform, we will get x2 of k to be 2 to the power k x2 at 0. So, that can be easily verified. Now, substituting x2 of k in the first equation, which is x1 of k plus 1 is minus x1 of k plus k times x2 of k is given by this expression. So, that is substituted 2 to the power k x2 of 0. Now, again taking Z transform both sides of this equation, we will get Z into Z transform of x1 minus x1 0 is minus Z transform of x1, and Z transform for this expression is minus Z times d by dz of the Z transform of 2 power k, that is Z by Z minus 2 into the initial condition. Now, collecting the Z transforms in one side and taking the inverse Z transform, we get the Z transform of 1 is given by this expression, and the inverse Z transform gives the equation 12. So, the solution, the inverse Z transform of 1 by Z plus 1 is given by this. So, this expression is the product of the two Z transforms, f of f suffix k and g suffix k are the inverse Z transform of this expression. So, we can use the convolution theorem to find the inverse Z transform of the expression 2 Z by Z minus 2 whole square plus Z plus 1. So, the convolution formula is given in the right hand side here, and the expression is given by this one. So, the solution x1 of k is given in the last line here. Now, we come to the control systems. Consider the non-autonomous control system in which the matrix A and B are functions of k, the time instances, and initial time instant is k0 and initial condition is x suffix 0. Now, making use of a similar step by step method, so if you calculate x at k0 plus 2, we will get this expression given in the last step. So, this is only substituting step by step. So, x at k0 plus n, that is at the nth time instant, is given by the formula as shown in the right hand side, and here the state transition matrix phi of k0 plus n comma m is given by this expression, where m is less than or equal to, it should be strictly less than, okay. M is strictly less than k0 plus n, because the right hand side it starts with k0 plus n minus 1 and decreasing up to capital M. So, M cannot be equal to this expression. Okay. So, by substituting k is equal to k0 plus n, we can see that the state transition matrix phi of km is a k minus 1 up to am, the product in the right hand side, and the solution x of k is given by the formula as shown in this expression 13, shown in the expression 15 here. The solution in the last step x of k0 plus n is given in this right hand side. So, we can easily compare it with the compact expression which is given in the equation 15 as the solution of the problem. So, now this expression is common to the time varying case or time invariant case. So, in the time invariant case, autonomous case, phi is replaced by simply a to the power this expression k0 minus I plus 1. So, that is the only difference. Wherever phi is there, we will replace it with a to the power k minus k0 here, and here we will replace it. So, that is for the time invariant case, and this is 15 is the general formula for the time varying case. Now, we define the controllability of the non autonomous system, time varying, sorry 1 minute Dinesh can cancel. So, now we will see the controllability of the autonomous system x of k plus 1 equal to a x of k plus b u of k. So, this system is said to be controllable if for any arbitrary state x 0 and x 1, two vectors in Rn. So, here we will consider A is a n cross n matrix, B is a n cross m matrix. So, two arbitrary vectors x 0 and x 1 both belong to the state space Rn. There exists a integer capital N, that is the final time capital N, and a sequence of control u0, u1 up to un minus 1, such that the solution of the system 16 satisfies the condition x of 0 equal to x 0 and x of capital N is x f, x suffix f is the final. So, the system is controllable for any two arbitrary vectors x 0 and x f given in the state space Rn. There exists an integer n as final instant and a sequence of control u1, u2 up to un minus 1, such that the solution satisfies the initial and the final conditions. So, here in all these problems we note that A should be a non-singular matrix, because we have seen that the state transition matrix for satisfying the properties, 4 properties, it should be a non-singular or invertible matrix. So, now we prove the theorem which is analogous to the continuous case, where we have defined the Gramian controllability Gramian matrix. So, the system where we have proved the Kalman theorem earlier. So, the system 16 is controllable if and only if the Kalman matrix B A B A square B up to A power n minus 1 B has rank n. So, the similar theorem we have proved it for the continuous case earlier. So, the proof is quite straightforward here. So, now the time instances are 0, 1, 2, 3 up to capital N. If you substitute each instant one by one, So, x of 1 is a x 0 plus b u 0. Similarly, x of capital N is a power n x of 0 plus etcetera, and we get the equation 17 by substituting step by step. Now, the definition of controllability is we have to find a integer capital N, so that the solution satisfies. We have to find an integer capital N as well as a sequence of control, that is u 0, u 1 up to u n minus 1, so that the solution satisfies the condition x of 0 is x 0 and x of capital N is x suffix n. So, we will see under the condition, the rank condition given in the last line, we can prove that the system is controllable. So, now x f, if we substitute x of capital N equal to x f in the equation 17 and taking this a to the power n x of 0 in the left hand side, we will get the first line here, x f minus a to the power n x of 0, it is equal to the remaining terms, which can be denoted in this following way. So, let us write the left hand side as x bar, which is a vector in Rn, and because x 0 and x f both are arbitrary, this x bar is also a arbitrary vector in Rn. So, the remaining terms in the right hand side can be written as b a b a to the power n minus 1 b here multiplied by u of n minus 1. We can note that the B matrix is multiplied by u of n minus 1. So, that is here A B matrix is multiplied by u n minus 2 etcetera. A to the power n minus 1 is multiplied by B matrix. A to the power n minus 1 B is multiplied by u of 0. So, this expression can be written in the form of equation 18. Now, the size of the matrix, if you call this as the U matrix, capital U, its size is n cross n into m, because B is a n cross m matrix and AB is a n cross m matrix etcetera. So, the size of this matrix capital U is n cross capital N into m. Now, U is a vector which is m cross 1 vector. So, each u is m cross 1 vector. So, the totally you have n into m cross 1 vector here in the equation 18. So, equation 19, it is simply a system of algebraic equation where x cap is a arbitrary vector, u is the matrix given here and small u is the vector of size capital N m cross 1. So, if the rank of this matrix U is n, then it is clear that there exists a solution for this system, because for existence of the solution of 19, the rank of U and rank of the augmented matrix U and x bar should be equal. And if the rank of U itself is n, then the system 19 will have a solution. There will be infinitely many solutions because of the size of this matrix. U is not a square matrix. So, it will have a solution means it will have infinitely many solutions. So, we get if the rank of this matrix is equal to n, then the system will have a solution, that is U. So, this sequence is defined from the equation 9. So, we will get the solution the small u n m cross 1 exist. From this we can get the solution of the discrete control for the discrete system. So, the converse part also can be proved analogous to the continuous case, that is, if the system is controllable, then the rank of this matrix should be equal to n. So, it is exactly similar analogous to the control the continuous control system. So, we need not repeat the same thing. So, with this I will complete the lecture for the discrete autonomous control systems. So, in the next lecture we will see the controllability of the discrete non autonomous control systems. Thank you.